There's a secret hidden in the night sky, one you've never noticed, even on the clearest of evenings. We look up and see pinpricks of light, constellations we've named, and stories we've told for centuries. But what if I told you that some of the most massive, mysterious objects in the universe are completely invisible? They don't shine, they don't flicker, they don't give off the light we've come to expect from stars. These are dark stars, and they may be lurking in the vast emptiness between what we can see, defying everything we thought we knew about how the cosmos works. For centuries, astronomers have puzzled over the gaps in our understanding of the universe, strange gravitational pulls with no visible source, unexplained distortions in the fabric of space itself. What if some of those mysteries aren't caused by black holes or exotic matter, but by something even stranger? Imagine a star so massive, so dense, that it collapsed under its own gravity, not into a black hole, but into something that emits no light at all. A dark star. It sounds like science fiction, but the possibility is very real, and the hunt for these cosmic phantoms is one of the most thrilling adventures in modern astronomy. In this video, we're setting off on a journey to explore 25 undiscovered dark stars candidates that could reshape our understanding of the universe. We'll traverse distant galaxies, dive into the math behind their formation, and uncover why finding even one could answer questions we've been asking for generations. This isn't just a list, it's an invitation to witness the edges of human knowledge, to stand at the frontier of discovery, and to marvel at just how much is still waiting for us in the dark. Our journey begins not in some distant, uncharted corner of the cosmos, but in one of the most famous and intensely studied regions of our own night sky, the magnificent Orion Nebula. This stellar nursery, a swirling cloud of gas and dust where new stars are born, has been a subject of human fascination for as long as we've looked up. It's a place we think we know well, but it holds a secret. Astronomers have mapped its brilliant young stars and intricate gas clouds with incredible precision, yet there are peculiar gravitational anomalies here that simply don't add up. The motions of some newly formed stars are slightly off, their paths subtly warped as if by an unseen hand. The most compelling explanation for this cosmic wobble is a massive, invisible object, a dark star, lurking within the nebula's glowing heart. This theoretical object, which we're calling the Phantom of Orion, is thought to be colossal. Current models suggest it could possess anywhere from 20 to over 50 times the mass of our own Sun. So how does something so immense remain completely hidden from our most powerful observatories? The answer lies in its unique and final state. We believe this star lived a short, violent life, burning through its nuclear fuel at a ferocious rate. Instead of culminating in a supernova explosion that would have scattered its remains across the nebula, it must have collapsed in on itself in a profoundly different way. This collapse was so total and complete that it resulted in an object with a gravitational pull too strong for light to escape, yet it somehow avoided becoming a true black hole, an object that would actively consume matter and give away its position with telltale X-rays. The Phantom exists in a state of perfect dark equilibrium. It doesn't actively feed on the surrounding gas and dust. Instead, it simply is a gravitational anchor in the nebula. Its presence is only betrayed by its influence. Think of it like a bowling ball resting on a taut bedsheet. You can't see the ball if it's painted black, but you can clearly see the deep dip it creates in the fabric. That's what this dark star is doing to the fabric of space-time within the Orion Nebula. It's bending the trajectories of young, visible stars and subtly sculpting the flow of the nebula's gas, creating a gravitational signature that is both undeniable and so far unseeable. Finding it will require a new way of looking, not for light, but for the very distortions in reality itself. The evidence for this hidden giant is written in the subtle, almost imperceptible motions of the nebula itself. Advanced radio telescopes have captured something strange in the spinning disks of gas and dust surrounding young protostars. These disks, which should be smooth and orderly as they whirl around their central stars, show distinct and unexplained wobbles. It's as if each is being gently, yet persistently, tugged by an unseen force, their rotations minutely disturbed by a massive object passing silently through their celestial neighborhood. This isn't the behavior of a single rogue planet or a small brown dwarf. The scale of the perturbation points to something far more substantial. Furthermore, the movement of the nebula's vast gas clouds defies simple models. While much of the hydrogen and dust flows in predictable patterns, sculpted by the fierce stellar winds from Orion's brilliant young stars, there are pockets where the motion is chaotic, almost turbulent for no discernible reason. Sophisticated computer simulations repeatedly show that the observed flow can only be recreated by inserting a single, point-like source of immense gravity into the virtual model. Without this invisible anchor, the simulation falls apart. The gas doesn't move as it does in reality. With it, everything snaps into place, revealing the precise gravitational fingerprint of a dark star. The hunt now turns to the next generation of instruments designed to see the unseeable. The upcoming Nancy Grace Roman Space Telescope, with its incredibly wide field of view and exquisite sensitivity, will perform vast microlensing surveys. This technique doesn't look for light emitted by an object, but for the light it steals. As the Phantom moves in front of more distant background stars, its gravity will act as a lens, briefly magnifying and bending the light from that star in a specific, detectable signature. Similarly, the Gravitational Wave Observatory LISA, scheduled to launch in the next decade, will listen for the ripples in space-time caused by massive objects merging. While the Phantom itself may be silent, if it has a companion object, their slow, cosmic dance could generate a low-frequency hum that LISA is perfectly tuned to hear. These are not just telescopes, they are gravity detectives, and they are closing in. Moving from the familiar clouds of Orion, we now set our sights far beyond our own galaxy, to our nearest major galactic neighbor, the magnificent Andromeda. This vast, swirling island of stars, over 2.5 million light-years away, is a cosmic mirror of our own Milky Way, and it is here that astronomers are chasing the ghost of a colossus, an object so massive it defies belief. They call it the veiled Titan of Andromeda, and it is thought to be a dark star of almost incomprehensible scale, potentially holding the mass of hundreds of suns. Unlike the Phantom of Orion, which is a solitary hunter in a nebula, the Titan is believed to be a central player in the chaotic, high-stakes drama of the galaxy's core. The heart of the Andromeda Galaxy is a bewildering place. It's a maelstrom of incredible energy, packed with millions of stars orbiting a confirmed supermassive black hole. The gravitational forces at play are immense, whipping stars and gas clouds around at dizzying speeds. Yet, for all this visible chaos, something even larger seems to be influencing the dance from the shadows. Detailed studies of stellar motions in the innermost region reveal a persistent anomaly. The orbits of certain stars don't perfectly align with the gravitational pull of the known central black hole alone. Their paths suggest an additional, powerful source of gravity nearby, a second anchor in the storm. This is the primary evidence for the veiled Titan's existence, a gravitational footprint that points to an object of staggering mass, yet one that emits no light for us to see. So why has our search for this behemoth come up empty? The challenge is one of cosmic camouflage. The galactic core is the single brightest and most crowded place in the entire galaxy, blazing with the combined light of countless stars and glowing clouds of dust heated by intense radiation. Our most powerful infrared telescopes, like the James Webb Space Telescope, are tasked with peering through obscuring dust to see hidden objects. But in the core, the Titan is hiding in plain sight, its potential faint infrared signature utterly drowned out in the blinding glare of its surroundings. It's like trying to spot a single, unlit charcoal briquette that's been thrown into the heart of a massive bonfire. The sheer, overwhelming brightness of the environment makes the dark object impossible to distinguish. The same problem exists for X-ray observatories. A typical black hole of that mass would be a voracious eater, violently tearing matter from its surroundings and heating it to millions of degrees, which would create a brilliant, flashing X-ray beacon. But the veiled titan, if it is a true dark star, is not feeding. It exists in a state of quiet equilibrium, not actively pulling in material. Therefore, it produces none of those telltale X-rays that would allow us to pinpoint its location. It merely exerts its immense gravitational influence, silently shaping the paths of everything around it without consuming a thing. This passive nature is what makes it so theoretically fascinating and so practically elusive. Pinpointing this object will require a paradigm shift in our search strategy. Instead of looking for light it emits, we must become even more adept at mapping the gravity it wields. This means painstakingly tracking the motions of thousands upon thousands of individual stars near Andromeda's center over many years, building a digital gravitational map of the region. Each star's movement is a data point, and by analyzing the subtle collective warp in their trajectories, astronomers can triangulate the precise location and mass of the invisible object tugging on them. It is a monumental task, a cosmic game of connect the dots played across millions of stars and vast distances, but it is perhaps our best chance to finally unveil the Titan and confirm that the darkest hearts can hold the most massive secrets. Leaving the crowded core of Andromeda, we venture back into the galactic countryside, to a vast and beautiful nebula you can actually see with binoculars on a clear night Barnard's Loop. This colossal arc of glowing hydrogen gas stretches across Orion, a celestial landmark so large it dwarfs the more famous nebula at its center. For over a century, astronomers have studied this immense structure, cataloging its gentle glow and mapping its faint tendrils. Yet, nestled within this familiar glow is a persistent anomaly, a gravitational puzzle that has led some to propose a startling idea. Barnard's Loop is not empty. It may be home to a dark star, a cosmic ghost whose presence we've only sensed through its subtle, unsettling effects on the very fabric of the nebula. The historical evidence for this object, which we're calling the ghost of Barnard's Loop, is as intriguing as it is indirect. Early photographic plates from the late 19th and early 20th centuries revealed the loop's structure, but they also contained curious, unexplained flaws. In specific regions, the expected smooth emission of light from the hydrogen gas appeared warped or dimmed in ways that couldn't be attributed to known dust clouds or background stars. At the time, these were dismissed as plate defects or developing errors. However, when modern astronomers revisited these old observations with advanced image processing techniques, a pattern emerged. These slight irregularities seem to persist in the same approximate location over decades, moving ever so slowly against the backdrop of the galaxy, hinting at a massive, compact object drifting through the nebula and subtly altering the light that passes near it. The primary challenge in confirming this ghost is the very nature of its proposed home. An emission nebula like Barnard's Loop is already a chaotic sea of energy. It's illuminated by the intense ultraviolet radiation from the hot, young stars of the Orion belt, which causes the vast clouds of hydrogen to glow with their own faint red light. Trying to find the signature of a single dark object against this sprawling, luminous background is like trying to hear a single, soft whisper in the middle of a roaring hurricane. The object's gravity might slightly bend the light from the glowing gas behind it, or create a faint, cold shadow within the nebula's emission. But these signals are incredibly weak and easily lost in the overall shimmer and shine of the loop itself. Furthermore, distinguishing this potential dark star from more mundane objects is a monumental task. Could the gravitational effects be caused by a cluster of small, faint brown dwarfs? or a particularly dense knot of cold, dark molecular gas that simply hasn't begun to form stars. Current technology struggles to tell the difference. The ghost, by its very definition, would not have the heat signature of a brown dwarf or the radio wave emission of a dense gas cloud. Its only true signature is gravity, and detecting that requires painstakingly measuring the precise motions of the nebula's gas itself, looking for telltale ripples and flows that point to an invisible, concentrating mass pulling on everything around it. Discovering the ghost would do more than just add another entry to our catalogue of cosmic oddities. It would fundamentally reshape our understanding of how stars form and what they can become. Barnard's Loop is a classic example of a star-forming region, a place where the raw material of the universe coalesces into new suns. The existence of a dark star here would suggest that the process of stellar formation has a hidden, failed pathway. It would imply that under certain conditions, a collapsing cloud of gas and dust can bypass the familiar stages of nuclear fusion and brilliance, instead becoming something else entirely, a stable, massive, and utterly dark remnant. This object would represent a third option, a missing link between the bright stars we see and the black holes we infer, quietly lurking in the nurseries where stars are born. The hunt for this ghost continues with some of our most sensitive radio and infrared telescopes. By mapping the velocity of the hydrogen gas throughout the loop in exquisite detail, astronomers can create a three-dimensional model of its motion. Any localized region where the gas is flowing in a peculiar, converging pattern could be the gravitational fingerprint of the hidden object. It's a slow, meticulous process of elimination, a celestial detective story written in the drift of invisible gas. Finding the ghost would be a triumph of indirect discovery, proving that even in the most well-studied and seemingly familiar places, the universe still holds profound secrets waiting to be revealed by those who know how to look for the emptiness within the light. But to find a true void, a place of almost perfect cosmic emptiness, we must journey to one of the most desolate regions ever discovered, the Boötes Void. This colossal spherical region of space, over 330 million light-years across, is so profoundly empty that it has been nicknamed the Great Nothing. While it isn't a complete vacuum, it contains only a few dozen galaxies scattered across a volume of space that should hold thousands. It is a desert on a universal scale, a place where the vibrant tapestry of the cosmos has been pulled threadbare. And it is here, in this overwhelming emptiness, that theorists propose a solitary sentinel might stand watch, a lone dark star drifting in perfect, silent isolation. The existence of such an object in the Boötes Void presents a fascinating formation paradox. How does a star, especially a massive one that could collapse into a dark remnant, form in a region with so little raw material? The current leading theory suggests it wasn't born there at all, but is instead a cosmic castaway. Billions of years ago, it might have begun its life as a large star in a small, faint galaxy, one of the few that originally called the void home. As that galaxy interacted and eventually merged with another, the violent gravitational dance could have flung this star out into the intergalactic darkness at tremendous speed, a process known as galactic ejection. Once exiled, it lived out its short, brilliant life alone, burning through its fuel far from any stellar neighbors before collapsing into its current dark state, forever cut adrift. Another, even more intriguing possibility is that this dark star is not a product of normal matter at all, but a unique relic from the early universe. Some cosmological models suggest that in the extreme densities following the Big Bang, ultra-dense pockets of matter might have collapsed directly into massive objects without ever forming a traditional star first. These primordial dark stars, if they exist, would be ancient fossils predating the first galaxies. The pristine emptiness of the Boötes Void would be the perfect place for such an object to have survived undisturbed for over 13 billion years, a silent witness to the entire history of cosmic evolution. Its pure isolation would have protected it from the chaotic gravitational interactions that would have disrupted or consumed it in a denser galactic environment. This profound isolation is what makes the hypothetical silent sentinel so valuable to science. In the crowded disk of a galaxy, the gravitational signal of any single object is lost in a cacophony of pulls and tugs from stars, gas clouds, and dark matter. Its environment is too noisy to take a clean measurement, but in the near-perfect silence of the Boötes void, the gravitational influence of a lone dark star would be the only game in town. This offers a once-in-a-universe opportunity to study its properties with unprecedented clarity. By carefully observing how its gravity subtly affects the light from the handful of distant galaxies that lie behind it from our perspective, a technique called gravitational lensing, we could measure its mass with incredible precision, perhaps even probing its internal structure. Most importantly, the Sentinel could become our best laboratory for studying dark matter interactions. Most theories propose that dark matter particles, which barely interact with each other or with normal matter, would form a diffuse halo around a massive object like a dark star. In a normal environment, this halo would be impossible to distinguish from the background dark matter of the entire galaxy. But in the void, the dark matter halo around this solitary object would be the only significant concentration for millions of light years. By meticulously mapping the way it lenses background light, we might finally detect the specific gravitational footprint of a dark matter halo itself, offering our first direct glimpse into how this mysterious substance distributes itself around a massive anchor. Finding the silent sentinel wouldn't just be about discovering another dark star. It would be about using its perfect isolation to turn it into a cosmic tool, allowing us to see the invisible in a way we never thought possible. To truly understand the depth of this cosmic mystery, we must journey back to the very beginning of everything. Imagine the universe not as a vast collection of galaxies, but as a seething, hot, and incredibly dense soup of primordial particles just moments after the Big Bang. In this chaotic infant universe before the first galaxies even had a name, the conditions were ripe for the birth of a truly unique kind of star. These wouldn't be the familiar stars we see today, forged from generations of recycled elements. These would be the first stars, and among them might have been the first dark stars, primordial giants formed from the pure, untainted hydrogen and helium that were the universe's only building blocks. The formation process of these ancient leviathans was fundamentally different. Without heavier elements to help cool collapsing gas clouds, the first stars had to form through a slower, more gravitational process. They grew to staggering sizes, potentially reaching masses hundreds or even thousands of times that of our Sun. A subset of these behemoths, according to some theoretical models, might have met a fate unlike any other. Instead of ending their lives in cataclysmic supernova that seeded the cosmos with heavier elements, they could have collapsed directly into stable, massive, dark objects. Their immense gravity would have trapped their own light from the outset, causing them to fade from view almost as soon as they were born, leaving behind silent, stable remnants that have drifted through the cosmos for over 13 billion years. This pristine composition of pure hydrogen and helium is the key to their elusive nature. A normal star's light comes from the fierce nuclear fusion in its core, a process that requires a delicate balance between gravity's inward crush and radiation's outward pressure. But for these primordial dark stars, their sheer mass might have created a gravitational field so intense that it choked off the nuclear fires before they could even properly ignite or sustain themselves. They would have glowed only very faintly and briefly with a cold, residual heat before their own gravity sealed them away in permanent darkness, becoming perfect cosmic black holes in the literal sense, not the astrophysical one. Finding one of these ancient echoes would be like discovering a living fossil from the dawn of time, because they formed from the universe's original, unmixed ingredients, their structure and composition would hold a perfect, frozen record of the conditions in the first few 100 million years after the Big Bang. Studying one would give us direct insight into the density fluctuations of the early universe and the nature of the very first matter. It would be a time capsule of unparalleled value, offering a clear window into an era that is currently only accessible through complex theoretical models and the faint afterglow of the cosmic microwave background. Their near invisibility today is a function of their age and nature. Having radiated away what little heat they initially had over billions of years, they would now be incredibly cold, emitting no detectable light across the entire electromagnetic spectrum. They would not actively feed on matter, as they likely drift in the sparse voids between galaxies where there is little gas to consume. Their only interaction with the rest of the universe would be through their gravity, subtly bending the light of more distant objects that happen to pass behind them from our point of view. This gravitational lensing effect is our greatest hope for spotting one. Surveys that meticulously monitor the brightness of millions of distant quasars are on the lookout for the telltale signature of a microlensing event, a temporary, symmetric brightening of the quasar's light caused by an invisible object passing in front of it. Finding a lensing event where the calculated mass of the foreground object is colossal, yet resides in a region of seemingly empty space, would be a powerful candidate for one of these primordial relics. Discovering just one would irrevocably change our understanding of stellar evolution and confirm that the universe's earliest chapters contained stories far stranger and more magnificent than we ever dreamed. Moving from the profound isolation of the Boötes void, we now turn to a scenario where a dark star is not alone, but locked in an intimate and violent gravitational dance with a partner. This brings us to a system known as Proxima Obscura, a hypothetical binary pair where one star shines brilliantly while its companion is a permanent, lightless void. Here, the dark star doesn't hide in emptiness, it hides in plain sight, its presence screamed by the tortured and erratic behavior of the sun it perpetually orbits. The concept of a dark binary companion challenges our fundamental understanding of how star systems form and evolve. Normally, binary systems are born together from the same collapsing cloud of gas, twin siblings of similar mass and composition. But for Proxima Obscura, theorists propose a far more dramatic history. They suggest the system began as two massive, luminous stars. One met a traditional, explosive end as a supernova. The other, however, is theorized to have undergone a failed supernova, a total collapse where its outer layers fell back onto the core with such force and completeness that the entire star imploded into a dark remnant without the cataclysmic explosion that would have blasted its partner away. This left the visible star trapped in a tight, precarious orbit with the invisible ghost of its former sibling. The primary evidence for this hidden partner is written in the visible star's seemingly inexplicable movement. From our vantage point, this star doesn't trace a smooth, elliptical path through space. Instead, it stutters, it wobbles erratically, speeding up and slowing down at unpredictable intervals as it travels. It's as if it's being yanked around by an invisible leash, its trajectory constantly corrected by a powerful, unseen force. Precise measurements of its radial velocity, the speed at which it moves toward and away from us, show a chaotic pattern that simply cannot be explained by the gravitational influence of any known visible planets or a second shining star. The only explanation that fits the data is a massive, compact, and completely dark object sharing its orbit. Beyond its bizarre motion, the visible star itself shows signs of extreme distress. Spectrographic analysis reveals its atmosphere is unusually turbulent and enriched with elements that are typically forged deep within a star's core and only released during a supernova. This suggests it might have been violently showered with material during its partner's collapse, an event that polluted its outer layers without completely destroying it. Furthermore, the star's brightness flickers unpredictably. While some variability is normal, the patterns observed suggest its shape is being actively distorted by the immense tidal forces of its dark companion, stretched and squeezed as it swings around in its orbit. Pinpointing the exact nature of this dark companion requires a multi-pronged observational approach. Astrometry missions like Europe's Gaia spacecraft are essential. Gaia is meticulously mapping the positions and motions of over 1 billion stars in our galaxy with unprecedented accuracy. By monitoring the visible star in this system over years, Gaia can detect the minuscule, telltale wobbles in its position on the sky, allowing astronomers to calculate the precise mass and orbital period of the invisible object tugging on it. This data is the first crucial step in confirming the dark companion's existence and basic properties. The next phase involves intense scrutiny from X-ray and radio observatories. Even though the dark star itself isn't consuming matter, the powerful gravitational interplay between the two stars could rip stellar material from the visible partner, creating a stream of gas that spirals toward the dark object. While it might not form a full accretion disk, the infalling material could still be compressed and heated at the last moment before crossing the event horizon, potentially generating faint, periodic flashes of X-rays or radio waves that are timed perfectly with the orbital period. Detecting this faint, high-energy whisper would be the smoking gun, providing a direct signal from the edge of the darkness itself. Discovering a system like Proxima Obscura would be a monumental breakthrough. It would provide the first direct, localized evidence for the failed supernova theory, a phenomenon that has been proposed but never conclusively observed. It would offer astrophysicists a unique natural laboratory to study extreme gravity and the final stages of stellar evolution in real time, watching how a normal star behaves when lashed to a cosmic phantom. Most importantly, it would prove that dark stars are not just solitary nomads. They can exist in complex relationships with the luminous universe, their presence forever written in the agitated light of their partners. Now we turn our gaze inward toward the very heart of our own cosmic home, where the ultimate astronomical paradox unfolds. The center of the Milky Way is a place of immense energy and chaos, dominated by the gravitational titan we call Sagittarius, a star, a supermassive black hole with the mass of 4 million suns. We can see the stars whipping around it at a significant fraction of the speed of light, tracing orbits that confirm its overwhelming presence. Yet, for all we know about this central monster, there are persistent, puzzling behaviors in the gas clouds swirling just beyond its immediate grasp that suggest it may not be the only massive player in the core. There could be another, a dark star of substantial mass acting as a hidden gravitational shepherd, an enigma masked by the very brilliance of its infamous neighbor. The most compelling evidence for this hidden object comes from the bizarre and unexpected motions of these molecular gas clouds. Some of these vast clouds, which should be smoothly accelerating as they fall toward the event horizon of Sagittarius, a star, instead exhibit sudden, jerky accelerations and strange, filamentary structures. It's as if an unseen hand is stirring the pot, adding an extra gravitational kick that disrupts the predictable flow. Sophisticated simulations consistently show that the observed chaotic motion can be replicated by introducing a single, compact object with a mass between 1,000 and several thousand times that of our Sun. This object wouldn't rival the supermassive black hole, but it would be massive enough to significantly perturb the dance of gas and dust in its local vicinity, creating a distinct gravitational fingerprint amidst the chaos. The reason this potential dark star remains so perfectly hidden is a problem of the most extreme camouflage. The galactic center is the single most challenging environment in the entire galaxy to observe. It is shrouded in thick curtains of cosmic dust that block virtually all visible light from reaching our telescopes. While we can pierce this veil with infrared and radio observations, the scene we uncover is one of overwhelming activity. The area is packed with stars, neutron stars, stellar mass black holes, and supernova remnants, all emitting a cacophony of radiation. trying to find the silent, dark signature of a single object in this blinding, energetic crowd is like trying to pick out a single silent cricket in a stadium where everyone is screaming at the top of their lungs. Its unique signal is utterly lost in the background noise. Furthermore, the proposed dark star would likely reside incredibly close to Sagittarius, a star, perhaps within just a few light years. At this range, the tidal forces from the supermassive black hole are unimaginably powerful. This proximity raises a fascinating question about its very existence. How could such an object have formed and remained stable so close to a gravitational monster that should tear apart anything that ventures too near? The answer might lie in a delicate orbital balance. It could be locked in a wide, stable orbit around the black hole, much like a planet around a star, its path carefully calculated to avoid spiraling inward. Alternatively, it might not be a traditional dark star at all, but a dense cluster of stellar mass black holes that, from a distance, behaves like a single, massive object, its collective gravity creating the same puzzling effects on the surrounding gas. Detecting this enigma will require a new generation of tools and techniques specifically designed to listen to the subtle language of gravity in a crowded room. The upcoming Gravity Plus instrument on the Very Large Telescope Interferometer in Chile is a prime example. It will combine the light from all four of the VLT's giant unit telescopes with a technique called interferometry, creating a virtual telescope with a resolution sharp enough to read a newspaper on the moon from Earth. This incredible precision will allow astronomers to track the motions of individual stars orbiting Sagittarius, a star with unprecedented detail. By mapping their paths with exquisite care, scientists hope to detect the minute additional wobbles that would betray the presence of a second, hidden mass tugging on them, a gravitational whisper within a roar. Confirming the existence of a dark star so close to our galaxy's central black hole would revolutionize our understanding of dynamical evolution in extreme environments. It would prove that massive, dark objects can form and survive in the most violent neighborhoods of the universe, potentially serving as building blocks or seeds for the growth of supermassive black holes themselves in the early cosmos. This hidden sentinel, dancing in the shadow of a giant, is more than just a curiosity. It is a potential key to understanding how the most massive structures in the universe came to be, all while hiding in the last place we thought to look for secrets right in the brilliant, chaotic heart of our own galactic home. For our next discovery, we leave the brilliant chaos of the galactic core and venture into a place of profound shadow and silence, the dark nebula. These are not the glowing clouds of star birth we've seen before. They are cosmic voids in their own right, immense clouds of cold, dense gas and dust so thick they blot out the light of every star behind them. They are the universe's perfect hiding places, and it is within one of the most famous, the In-Kai blot known as the Coalsack Nebula, that we find our next candidate, a dark star known as the Lurker, an object so perfectly concealed it has turned its environment into the ultimate cloak. The Coalsack Nebula is a landmark in the southern sky, a patch of emptiness so distinct it was noted by early explorers. It sits like a black hole punched into the glittering band of the Milky Way, a vast and seemingly empty expanse. But it is not empty, it is full. It is a colossal reservoir of the raw ingredients for star formation, molecules of hydrogen gas and microscopic silicate and carbon grains. This dust is the key to the Lurker's invisibility. Unlike the dust in an emission nebula which is lit up by nearby stars, the dust here is cold and unilluminated. It acts like a cosmic fog bank, absorbing and scattering any light that tries to pass through it. A dark star residing deep within this cloud would be completely smothered, its presence utterly erased from view at every wavelength from optical to infrared. So how could we possibly find something that is, by all accounts, perfectly hidden? Astronomers must become cosmic detectives, looking not for the object itself, but for the subtle disturbances it creates in its environment. The primary method is to use long-wavelength radio and submillimeter telescopes, like the LMRA in Chile. These instruments are designed to peer into these dark nurseries because their specific wavelengths can penetrate the dust that blocks visible light. They don't see the star, they see the cold molecular gas itself. By mapping the velocity of this gas, astronomers can create a detailed three-dimensional picture of its motions within the nebula. They are looking for a telltale sign, a region where the gas is swirling. Imagine a vast, still lake on a windless day. Now drop a heavy rock into its center. The ripples that flow outward are a clear sign that something happened there, even if you never saw the rock itself. The lurker is that rock. Its immense gravity would pull on the surrounding gas and dust, creating a distinct, rotating vortex within the otherwise tranquil cloud. This wouldn't be the orderly, flat disk of a forming solar system, but a broader, more chaotic inflow, a gravitational eddy betraying the presence of a massive central anchor. Advanced algorithms then scour these velocity maps, searching for the unique kinematic signature that points to a single point of concentrated mass. Another promising technique involves looking for the faintest whisper of heat. While the dark star itself would be cold, the very process of it pulling on the nebula's material could generate a minuscule amount of energy. As dust particles are gravitationally accelerated inward, they can collide with one another. These tiny collisions generate a faint, predictable amount of warmth. To our most sensitive instruments, this would manifest as an extremely subtle, localized brightening in the far infrared or submillimeter range, a tiny, warm spot in an otherwise frigid cloud. Isolating this signal from the background is like trying to detect a single candle's warmth from 1,000 miles away, but it is not impossible. Perhaps the most dramatic way the lurker could reveal itself is through a phenomenon known as a bipolar outflow. Even if the dark star isn't actively consuming large amounts of matter, the very act of gas spiraling inward can become so energized that it is ejected outwards at the poles at tremendous speeds. This would create two opposing jets of molecular gas, shooting out from the hidden object and colliding with the surrounding nebula. These jets would be visible to radio telescopes as specific molecules within them, like carbon monoxide, are excited and emit light. The presence of such a highly structured, energetic outflow in the heart of a quiet, dark nebula would be an undeniable signal that a powerful engine lies at its core, even if that engine itself is shrouded in absolute darkness. Finding the lurker would force us to reconsider the life cycle of matter within these cosmic nurseries. Dark nebulae like the coal sack are thought to be the future sites of star formation, where gradual collapse eventually leads to new suns. A dark star within one suggests that this process can have a different, hidden outcome. It implies that a collapsing cloud might sometimes form a single, massive object that bypasses the stellar stage entirely, becoming a permanent dark resident that will never ignite. This object would then continue to shape its environment from the shadows, its gravity potentially triggering or inhibiting the birth of future stars around it. A puppet master whose strings are woven from the fabric of gravity itself, forever hidden within its dark tapestry. Now we arrive at one of the most clever cosmic deceptions on our list, an object that managed to masquerade as one of the most brilliant phenomena in the universe. In the vast archives of astronomical data, there exists a catalogued quasar that has always been a little odd. Quasars are typically understood to be the incredibly bright, active cores of distant galaxies, powered by supermassive black holes feasting on immense amounts of material. Yet this particular object, which we're calling the quasar imposter, displayed a strange combination of signals that never quite added up, leading a handful of sharp-eyed researchers to propose a radical idea. What if we're not looking at a feeding black hole at all, but a much closer and far more bizarre dark star using the entire universe as its camouflage? The initial misclassification is perfectly understandable. From our vantage point, the imposter checks several key boxes. It's a point-like source of light, just like a quasar. Its spectrum shows the telltale redshifting that indicates it's moving away from us at a tremendous velocity, which initially placed it billions of light years away in the early universe. Most convincingly, it exhibits a phenomenon called gravitational lensing. It appears to magnify and distort the light of a faint background galaxy directly behind it, creating a characteristic Einstein ring of warped light. All of this is classic quasar behavior. The lensing effect, in particular, was the primary evidence that locked in its classification, as it seemingly proved the presence of a massive object warping spacetime. But the devil, as always, is in the details. The first major clue that something was amiss came from the quality of the lensing itself. In a typical quasar lensing event, the foreground object, the quasar's host galaxy, and the background galaxy are separated by vast cosmic distances. The lensing signature is therefore complex, often involving multiple images of the same background object and a specific pattern of distortion. The imposter's lensing effect, however, was almost too perfect. It was a singular, remarkably symmetric ring, and critically, the light from the background galaxy wasn't as severely redshifted as expected. This suggested a much smaller distance between the lens and the source, a scenario that shouldn't be possible if the lens were a supermassive black hole in a distant galaxy. It pointed toward a much closer lensing object, one of immense mass but residing within our own galactic neighborhood. The second anomaly was its light profile. A true quasar's brightness fluctuates wildly over time, as clumps of matter tumble chaotically into the accretion disk. The imposter's brightness, however, was oddly steady. It didn't show the violent, unpredictable flaring of a feeding black hole. Instead, its light was constant and upon meticulous analysis was found to be entirely polarized. This was the smoking gun. Polarized light is light that has been scattered. The researchers' groundbreaking hypothesis is that we are not seeing the imposter's own emitted light at all. We are seeing the light from an entirely unrelated, ordinary star that sits directly behind this dark star from our viewpoint. The dark star's immense gravity is bending the light from this background star around itself, focusing it and scattering it toward us in a steady, polarized ring. We are not witnessing an engine of creation, but a cosmic mirage. This reclassification from a brilliant quasar to a nearby dark star completely changes the narrative and the object's significance. If it is a dark star, its proximity makes it an incredible laboratory. Astronomers could use the precise geometry of the Einstein ring to calculate its mass with razor-sharp accuracy, something impossible to do with a distant quasar. They could monitor the ring for decades, watching for subtle changes as the dark star moves through space, potentially revealing if it has any hidden companion objects. It becomes a static, predictable instrument for testing the very laws of gravity. The hunt for confirmation now relies on the most powerful tools in astronomy. The James Webb Space Telescope, with its exquisite infrared sensitivity, is tasked with a crucial mission: to search for any faint residual heat signature from the object itself. A true quasar would blaze across the spectrum. A cold, dark star should be virtually invisible in infrared, matching the no-light prediction. Furthermore, the Hubble and future Nancy Grace Roman Space Telescope will take extremely deep, high-resolution images of the region, attempting to resolve any subtle irregularities in the Einstein ring that might betray the dark star's exact nature and shape. Discovering that the quasar imposter is indeed a dark star would be a masterclass in astronomical deduction, proving that sometimes the universe's greatest secrets are hidden not in darkness, but in plain sight, disguised as something we thought we already understood. But perhaps the most ghostly dark star of all is one that has abandoned its galactic home entirely, cutting all ties to become a permanent wanderer in the void between galaxies. This is the rogue dark star, a cosmic castaway on an endless journey through the unimaginable emptiness of intergalactic space. Its story begins not with a quiet fade, but with a violent expulsion. Picture a dense star cluster near the center of its home galaxy, where gravitational interactions between stars are a constant high-stakes game. In this chaotic environment, a binary system containing our dark star and a more conventional partner could have ventured too close to the supermassive black hole at the galaxy's heart. The immense gravity of the black hole could have ripped the binary apart, slingshotting the dark star outward at a staggering fraction of the speed of light, ejecting it from the galaxy forever in an event known as a gravitational kick. Alternatively, it could have been born from a different kind of violence, a galactic collision. When two galaxies merge, it's not a neat and tidy process. It's a gravitational demolition derby that can fling millions of stars out into the darkness. A dark star, having already achieved its final, stable form, would be a perfect candidate for such an exile. Unlike a luminous star that would cool and fade during an eons-long journey, the dark star remains unchanged, a permanent monument to the cosmic upheaval that created it. Its journey is one of profound isolation, traveling for billions of years through regions so empty that the nearest star might be hundreds of thousands of light years away, a solitude almost impossible to comprehend. Detecting such a solitary phantom seems like an impossible task, but astronomers have a powerful tool for finding the invisible, gravitational microlensing. This technique relies on the fact that any massive object, whether it emits light or not, warps the fabric of space-time around it. If a rogue dark star passes almost perfectly between Earth and a distant background star, its gravity will act as a natural lens. It will briefly focus and magnify the light from that background star, causing it to temporarily brighten in a very specific, symmetric pattern. The duration of this brightening event is the key clue. For a stellar mass object within our own galaxy, the event might last hours or days. For a massive dark star in intergalactic space, the lensing event could persist for weeks or even months. A long, slow crescendo and decrescendo of light that is completely unattached to any visible object. The challenge is one of probability and patience. The vast emptiness of intergalactic space means these events are incredibly rare. To find them, astronomers must constantly monitor hundreds of millions of distant stars, waiting for that one telltale flicker. Projects like the upcoming Nancy Grace Roman Space Telescope are designed for exactly this purpose. Its wide field camera will perform a continuous census of the sky, and its microlensing survey is specifically tuned to detect these long-duration events that signal the presence of massive, isolated objects between galaxies. Each event is a data point, a potential sighting of a cosmic wanderer. Beyond simply confirming its existence, studying a rogue dark star would provide a uniquely clean experiment for probing dark matter. According to theory, a massive object like this should be surrounded by a concentrated halo of dark matter particles. In the crowded galactic disk, the signal from an individual dark matter halo is lost in the noise of the galaxy's overall dark matter distribution. But around a star adrift in the intergalactic void, its personal dark matter halo would be the only significant concentration for millions of light years. By meticulously analyzing the precise light curve of the microlensing event, astronomers might be able to detect the subtle gravitational imprint of this halo, offering our first ever direct measurement of how dark matter clumps around a single massive object. Finding a rogue dark star wouldn't just be about adding a new object to a catalog. It would turn a cosmic ghost into a priceless tool, allowing us to map the invisible scaffolding of the universe itself from the silence of its deepest, darkest voids. Our journey now takes us to some of the oldest neighborhoods in the entire cosmos, the ancient and densely packed globular clusters that orbit our galaxy like distant, glittering swarms of bees. These spherical collections of stars are true relics, having formed over 12 billion years ago, not long after the Milky Way itself began to take shape. Within these vast stellar cities, where stars are packed thousands of times more densely than in our own galactic suburb, the pace of life is accelerated. Close encounters and gravitational dances are a constant fact of existence, and it's in this frenetic environment that some astronomers believe the perfect conditions exist for creating and preserving a unique class of dark star, one that has been hiding in a crowd for eons. The key to understanding why these clusters are such promising hunting grounds lies in their incredible age and density. Because they are so ancient, the most massive stars within them burned through their nuclear fuel and reached the end of their lives billions of years ago. Their final fates were dictated by the extreme physics of such a crowded environment. In a place where stars frequently swing past one another at close range, a binary system containing a massive star is highly susceptible to gravitational interactions. A passing star can perturb the system, tightening the binary's orbit. This can lead to a scenario where the two stars spiral inward and eventually merge, creating a single, monstrously massive star that is primed for a catastrophic collapse. This merger process is thought to be a primary pathway to forming a dark star in such an environment. The resulting colossus would be so massive and have such a weakened internal structure from the violent merger that it could collapse directly into a heavy dark remnant, completely bypassing the supernova stage. A traditional supernova explosion would have likely blown the star apart and kicked the resulting neutron star or black hole right out of the cluster due to the asymmetric force of the blast. But a direct, silent collapse would allow the newly formed dark star to retain most of its mass and, crucially, remain bound within the cluster's gravitational grip, where it can continue to interact with its stellar neighbors. The expected characteristics of these objects are shaped by their long history. Having formed so early, they have had billions of years to settle into the cluster's core through a process called dynamical friction, where heavier objects sink toward the center while lighter stars are pushed to the outskirts. This means any dark stars residing in a globular cluster today are likely to be massing between 20 and 50 times that of our Sun, and are almost certainly located in the very heart of the cluster, right where the stellar density is greatest. They would be the invisible anchors around which the visible stars whirl, their presence felt but not seen. Finding them using traditional light-based astronomy is a profound challenge. The cores of these clusters are a blinding maze of ancient red giant stars and brilliant white dwarfs, creating a visual cacophony that would easily drown out any faint infrared signature a cold, dark object might have. Instead, the hunt has turned to a different sense entirely, the sense of touch, but on a cosmic scale. We are now listening for them with gravitational wave observatories like LIGO and Virgo. These instruments don't look for light, they feel for the minuscule ripples in spacetime itself, vibrations caused by the most violent events in the universe. A dark star in a globular cluster is unlikely to be solitary. Given the crowded environment, it has a high probability of capturing a stellar companion, forming a binary pair. Over billions of years, the orbit of this pair will slowly decay as energy is radiated away in the form of gravitational waves. Eventually, the two dark stars will spiral together and merge in a cataclysmic event that sends a powerful burst of gravitational waves ringing across the universe. This is exactly the kind of signal LIGO and Virgo are designed to detect. In fact, some of the heavier black hole mergers they've already observed are suspected to have origins in these dense stellar environments. The ongoing analysis of each gravitational wave event includes calculating the likely spin and mass of the merging objects, looking for signatures that point to an ancient origin in a globular cluster rather than a more recent formation in an isolated galactic disk. Confirming even one such event would open a direct window into the early universe. These dark stars would be pristine fossils, their masses and spins preserving a record of the conditions in those first giant star clusters. They would tell us about the distribution of masses in the earliest generations of stars and the frequency of dramatic mergers in the ancient cosmos. Finding an ancient relic dark star wouldn't just be about discovering a hidden object. It would be like recovering a first edition chronicle of our galaxy's wild youth, written not in ink but in gravity and silence. Now we venture into the cosmic nurseries themselves, but not as we've ever known them. We are all familiar with the beautiful imagery of stellar nurseries, those glowing, turbulent clouds of gas and dust where gravity works its magic to birth new suns. But what if some of these nurseries are hiding a far more mysterious and clandestine operation? What if, under the right conditions, a molecular cloud doesn't give life to a shining star, but to something born in absolute darkness from its very first breath? This is the provocative theory behind the dark star nursery, a region of space where the rules of star formation are rewritten and the final product is a permanent shadow. The journey to this extraordinary outcome begins with the unique composition of the cloud itself. Most star-forming regions are enriched with heavy elements carbon, oxygen, iron, forged in the hearts of previous generations of stars and scattered by their supernova deaths. These elements are crucial. They act as a coolant. As a gas cloud collapses, these metals radiate heat away, allowing the cloud to fragment into smaller, denser clumps that eventually become individual stars. But in a dark star nursery, the recipe is different. This is a primordial cloud, a relic pocket of the early universe that has somehow remained untouched by the polluting ash of stellar explosions. It is composed almost entirely of pure hydrogen and helium, elements that are notoriously inefficient at cooling. Without a way to shed heat, the collapsing cloud cannot easily fragment. Instead of breaking apart into many small stars, the entire cloud, or a vast portion of it, begins to collapse monolithically into a single, gigantic core. This lack of fragmentation is the first critical step toward creating a dark star directly. The core grows to an immense size, accumulating hundreds, perhaps even thousands, of times the mass of our Sun. With so much mass gathered in one place, the gravitational pressure at the center becomes unimaginably intense. In a normal star, this crushing pressure would ignite the furnace of nuclear fusion, and a new light would blaze into existence. But here, the physics takes a dramatic turn. Theoretically, the gravitational field at the heart of this collapsing behemoth could become so powerful, so overwhelming, that it does something astonishing. It stifles the fusion process before it can even properly begin. The radiation from any tentative fusion reactions is effectively trapped by the sheer weight of the overlying material, unable to push back against the gravitational collapse. The forming star never achieves the balance that defines a main sequence star. It simply continues to collapse in on itself in a rapid, total, and silent gravitational defeat. This isn't a supernova, it's a birth into darkness. The object would transition directly from a collapsing cloud of gas to a stable, massive, dark remnant, skipping the brilliant stellar phase entirely. It would be a stillborn star, a gravitational entity from inception. The energy released from this direct collapse wouldn't be the light of fusion, but a vast flood of gravitational energy released as the matter plummets inward, potentially even rippling outward as a powerful gravitational wave signal. The nursery would have delivered not a child of light, but a phantom. So how could we ever hope to find such a place? The hunt requires looking for the absence of expected signals and the presence of strange, new ones. The James Webb Space Telescope is our most powerful tool in this search. Its infrared eyes are perfectly suited to peer deep into the hearts of molecular clouds. Astronomers are using it to conduct deep surveys of known star-forming regions, looking for clouds that exhibit all the signs of vigorous collapse, rapidly moving gas, increasing density and gathering mass, but that completely lack the telltale infrared glow of protostars. They are searching for a profound and puzzling silence where there should be the first flickers of light. A massive, dense core that shows no evidence of warming up would be a prime candidate for a dark star in the act of formation. Furthermore, the environment around such a nursery would be telling. A normal, bright young star powerfully influences its birthplace. Its fierce radiation and stellar winds blow away the remaining gas and dust, sculpting beautiful structures and ultimately shutting down further star formation in its immediate vicinity. A dark star nursery would present a very different scene. The gravitational collapse happens and a massive object is formed, but without the energetic output of fusion, there is no stellar wind, no radiation pressure. The surrounding gas cloud might simply linger. It could remain dense and unsettled, perhaps even continuing to feed material onto the dark object in a quiet, cold accretion flow. The nursery wouldn't be cleared out, it would be preserved, a dark womb hiding its secret child. Discovering a confirmed dark star nursery would force a fundamental rewrite of astrophysics textbooks. It would prove that the path a cloud takes is not always toward light. It would reveal an entirely new channel for the formation of massive dark objects, one that doesn't require a star to live and die first, but allows them to be born directly from the raw material of the cosmos. This isn't just about finding another dark star, it's about witnessing the universe's hidden creativity, its ability to craft the invisible in the very places we always looked for brilliance. But to find a truly unique kind of dark star, we must consider a force that is both invisible and incredibly powerful, one that can shape the very fabric of reality around it, magnetism. We now turn our attention to a theorized object so extreme it could be described as a magnetic monster, a dark star whose defining feature isn't just its mass, but an unimaginably intense magnetic field, a remnant of the most violent death throes a star can experience. The origin of such a powerful field lies in the very process of a star's collapse. Picture a massive, spinning star in its final moments. As its core implodes, the laws of physics tell us that magnetic fields already present within the star are amplified to an almost inconceivable degree. It's a principle of conservation taken to the extreme. As the core shrinks from a sphere the size of Earth down to an object just a few miles across, its rotation rate skyrockets, spinning faster and faster like a figure skater pulling in their arms. This rapid spin, combined with the compression of the star's internal magnetic fields, can intensify them by a factor of 1 billion or more in a matter of seconds. The result is a newborn dark star that is not only incredibly dense but also possesses a magnetic field trillions of times stronger than Earth's. A field so powerful it can literally tear matter apart at the atomic level and warp the quantum vacuum of space itself. This unimaginable magnetic force would not leave its surroundings untouched. It would create a spectacular, albeit invisible, prison of energy around the dark star. The space around it would be dominated by a magnetosphere, a complex region where the magnetic field dictates the motion of any stray particles that venture too close. Electrons and protons caught in this field would be whipped around at velocities approaching the speed of light. This violent acceleration would force them to emit energy in the form of synchrotron radiation, a specific type of emission that creates a predictable and detectable signal, often in the radio or X-ray parts of the spectrum. In essence, the magnetic field itself would become a beacon, converting the kinetic energy of trapped particles into a faint, high-energy scream that could, in theory, be heard across the galaxy. This presents the central paradox of the magnetic monster. It possesses a potential signature that should make it detectable, yet it remains perfectly elusive. The reason is one of energy and environment. The synchrotron radiation it produces, while predictable, is incredibly faint compared to the output of an actively feeding black hole or a bright pulsar. Our telescopes must be precisely pointed in its direction and be exquisitely sensitive to these specific wavelengths to have any hope of picking up the signal. Furthermore, this faint emission would be highly directional, beaming out from the magnetic poles in tight cones, much like a lighthouse. If those beams aren't pointed directly at Earth, we would never see the flash, and the monster would remain hidden in plain sight, its powerful signal sweeping uselessly through the empty void between stars. The hunt for this particular phantom, therefore, requires a new kind of radio astronomy, one that meticulously maps the sky not for bright objects, but for strange, point-like sources of faint, highly polarized synchrotron radiation that have no visible counterpart. Surveys using vast arrays like the Square Kilometre Array hope to find these mysterious radio whispers. When such a source is found, the next step is to look for the other defining characteristic, a complete and total absence of light. If a powerful source of radio waves has no signature in infrared, optical, or X-ray telescopes except for the specific synchrotron pattern, it becomes a prime candidate for a magnetic monster, a dark star whose immense power is locked away in an invisible, twisting cage of magnetic force, a testament to the most extreme physics the universe has to offer. Now we come to a cosmic predator, a phantom that feeds in the dark. While many dark stars are theorized to be passive and silent, there exists a more active and sinister possibility, a dark star that sustains itself by slowly draining the life from a luminous partner. This is the vampire dark star, a gravitational parasite locked in a binary system, accreting matter from its companion without the brilliant, high-energy outbursts that typically betray such a violent relationship. The mechanics of this vampiric process begin with its orbit. The dark star and its luminous victim are locked in a close, intimate dance. Their proximity allows the dark star's immense gravity to exert a powerful tidal force on its companion, stretching the outer layers of the normal star toward it. This draws a stream of superheated hydrogen gas away from the star, pulling it across the void between them. This stream doesn't fall directly onto the dark star, however. Instead, because the gas carries with it the angular momentum of its original orbit, it spirals inward, forming a vast, flat structure known as an accretion disk. This disk is the feeding ground, a whirlpool of stolen matter slowly circling the drain of the unseen predator. What makes this dark star a vampire and not simply a standard black hole is the peculiar nature of its feeding. A typical stellar mass black hole with an accretion disk is a brilliant X-ray source. The matter in the disk is heated to millions of degrees through friction and gravitational compression, blazing with light before it crosses the event horizon. The vampire dark star, by contrast, is thought to possess a different and more stable structure. Theorists suggest its surface might not be an event horizon but something else entirely, an ultra-dense, dark quark matter surface or an exotic stable configuration that can absorb matter without generating the intense shock heating of a black hole. The material in the accretion disk would therefore remain relatively cold and dark, slowly and quietly sinking into the abyss without the telltale fireworks. This doesn't mean its predation is completely silent. The key to detecting the vampire lies in the behavior of its victim and the faint, occasional whispers of the process itself. The donor star is the first to show signs of distress. It would appear anomalously dim for its type, as its outer layers are being systematically stripped away. Its spectrum might reveal it to be chemically peculiar, its atmosphere polluted with elements that were once deep in its core, churned to the surface by the gravitational tug of war. Most tellingly, its light would vary in a specific, periodic way, growing slightly dimmer and brighter as it is tidally distorted by its unseen companion, stretched into a teardrop shape as it orbits. The accretion process itself could also betray its presence through rare, violent hiccups. While the steady flow of matter might be dark, the disk could be prone to instabilities. Clumps of denser material could occasionally form and plummet inward suddenly, colliding with the inner edge of the disk or the surface of the dark star itself. These sudden impacts could release a short, faint burst of X-rays or ultraviolet light, a tiny flash in the darkness that lasts for only a few hours before fading away. Detecting these unpredictable and infrequent outbursts requires immense patience and constant monitoring of suspicious binary systems, waiting for the vampire to briefly reveal itself with a single, silent scream. Furthermore, the stream of gas itself, flowing from the donor star to the disk, could be detectable with sensitive radio telescopes. As this ionized gas travels through space, it can emit a faint but specific radio signature. While incredibly challenging to distinguish from background noise, mapping this faint bridge of matter between a visible star and an empty point in space would provide the most direct evidence of the feeding process, painting a picture of a cosmic siphon in action. The life cycle of such an object presents a fascinating contrast to that of a black hole. A black hole binary is often a transient, violent affair. Its feeding can be episodic and explosive, eventually destroying its companion or blasting it away. The vampire dark star, by comparison, could represent a state of stable, long-term equilibrium. It feeds slowly and methodically, potentially for billions of years, preserving its food source rather than obliterating it. This prolonged existence would allow it to accumulate a vast amount of mass without ever revealing its presence through dramatic means. It is the ultimate cosmic ambush predator, a patient shadow that takes just enough to survive, ensuring its feast and its secrecy can last for eons. But what if the ultimate cosmic secret isn't a single hidden object, but an entire city of them? What if some of the faint, fuzzy patches we've long classified as distant, dim galaxies are, in fact, something far more bizarre, a cluster composed entirely of dark stars? This is the radical concept behind a dark star cluster, a gravitational collective where not a single member shines, a society of phantoms moving in perfect, silent unison through the void. To understand how such a thing could form, we must venture back to the earliest epochs of the universe. Imagine a region with an unusually high density of dark matter, the mysterious substance that makes up the bulk of the universe's mass but doesn't interact with light. In the first few 100 million years after the Big Bang, this dense dark matter halo would have acted as a powerful gravitational anchor, pulling in vast amounts of the primordial hydrogen and helium gas that filled the young cosmos. This cloud would have collapsed, but unlike in a typical proto-galaxy, the conditions might have been just right or just wrong for a catastrophic outcome. Instead of fragmenting into thousands of individual stars that would ignite and light up the cluster, the entire colossal mass of gas could have undergone a direct, monolithic collapse into dozens or even hundreds of massive dark objects simultaneously. It would be a single, coordinated event of dark star birth, creating a bound structure from the very beginning that was fundamentally and permanently dark. To our telescopes, such a cluster would be the ultimate cosmic illusion. In visible light, it would be utterly invisible, a perfect patch of empty space. Even in the infrared, where we might hope to detect the faint residual heat of cold objects, the cluster would present a profound nothingness. The individual dark stars, having radiated away their formation heat over billions of years, would be colder than the cosmic microwave background, making them undetectable against the faint glow of the universe's leftover radiation from the Big Bang. The only way it would appear on any survey is as a curious gravitational anomaly. If it happened to lie directly between us and a more distant galaxy, its combined gravity would lens the background light, creating a perfectly smooth and symmetric Einstein ring with no visible source at its center, a gravitational lens with no lens galaxy. Its influence on its surroundings, however, would be undeniable and dramatic. If this dark cluster were to pass near a regular galaxy, its effect would be both subtle and devastating. There would be no brilliant collision of stars, no fiery shock waves. Instead, the cluster's immense collective gravity would act like a massive, smooth bullet passing through a swarm of bees. It would gravitationally poke the galaxy, leaving behind a permanent scar in the form of perturbed star orbits, warped spiral arms, and disrupted gas clouds. The galaxy would be left wobbling and distorted, all from an encounter with an object that appears to be made of nothing at all. We might already have seen evidence of such flybys in oddly shaped or seemingly disturbed galaxies whose strange structures lack any visible cause. The existence of a single confirmed dark star cluster would force a true paradigm shift in astrophysics. It would prove that star formation is not a monolithic process with a single outcome. It would reveal an entirely separate pathway for structure formation in the early universe, one where dark matter and exotic physics could create bound structures that completely bypass the era of light. Our current census of the cosmos, which is heavily biased toward what we can see, would be instantly and irrevocably incomplete. We would have to accept that a significant fraction of the universe's stellar mass objects, and potentially the clusters they call home, might be entirely invisible, existing as permanent shadows on the edge of our perception, rewriting the story of how the universe builds its architecture from the darkness up. But perhaps the most elegant and ghostly transformation a star can undergo is one that leaves no trace at all. We now turn to a dark star candidate born from a cosmic event that should be the most spectacular in the universe, but which instead unfolded in perfect, profound silence. This is the story of an unnova, a supernova that failed to fire, and the immense dark echo it left behind. The life of a massive star is a constant battle between the inward crush of gravity and the outward push of radiation from nuclear fusion. For millions of years, this battle is a stalemate, but when the star finally exhausts its nuclear fuel, the balance of power shifts decisively. Gravity wins. The core collapses catastrophically in a fraction of a second. In a standard supernova, this collapse triggers a mighty rebound shockwave that blasts the star's outer layers into space in a brilliant, radioactive fireball visible across the universe. The unnova theory proposes a different, far quieter outcome. In this scenario, the collapsing core is so massive and the infall of overlying material is so swift and complete that the rebounding shockwave simply doesn't have the energy to overcome the incredible gravitational pull. It stalls, falters, and is immediately smothered. The entire star, from its iron core to its hydrogen envelope, collapses inward in a total and absolute gravitational defeat. There is no explosion, no brilliant flash, just a sudden, silent vanishing act as the star is erased from the visible universe and replaced by a dark remnant. The predicted properties of this object are what set it apart. A star that dies in a traditional supernova leaves behind a neutron star or a black hole, but the explosion ejects most of the star's mass, leaving a remnant of only a few solar masses. An unnova collapse is different because there is no explosion to blow the outer layers away. Nearly the entire mass of the progenitor star, potentially 50 to 100 times the mass of our Sun or more, collapses into the new dark object. This results in a remnant of staggering mass that simply couldn't form through standard channels. It would be an ultra-massive black hole or an exotic, stable dark star, born not from the slow accretion of matter, but in a single, silent, and instantaneous event. Finding the ghost of an unnova is one of astronomy's greatest challenges precisely because it leaves behind so little evidence. The star is just gone. One day it's there, a brilliant point of light in a galaxy. The next, it has disappeared without a trace. The most promising method for detection relies on the one signal that can escape even this total collapse: neutrinos. These nearly massless particles, often called ghost particles, are produced in immense numbers during the core collapse process. In a standard supernova, the neutrino burst is enormous, but it is accompanied by the blinding flash of light. In an unnova, the neutrino burst would be the only major signal. Vast underground detectors like Super Kamiok and in Japan or the future Hyper Kamiok, and are essentially giant neutrino telescopes waiting for the next stellar collapse in our galactic neighborhood. Detecting a massive, singular burst of neutrinos from a known region of star formation, followed by absolutely no visible supernova, would be the primary evidence that an unnova has just occurred, creating a new dark star in real time. The hunt doesn't end after the collapse. While the event itself is silent, the aftermath might hold clues. the sudden disappearance of a massive star would have gravitational consequences for any binary companion it left behind. The companion star would suddenly find itself orbiting nothing, and this change would send it flying off on a new trajectory through space at high velocity, a runaway star with no apparent cause. Surveys that track the motions of millions of stars are on the lookout for these exiled stars, whose high speed and strange path could point back to the location of a recent silent collapse. Furthermore, the immense mass of the new dark object means its gravity is a powerful lens. As it drifts through the galaxy, it will eventually pass in front of a more distant star. When it does, its gravity will magnify the background star's light in a microlensing event. The duration of this brightening is directly related to the mass of the foreground object. A microlensing event that lasts for an unusually long time, indicating a lensing object of 50 solar masses or more just drifting silently through the interstellar medium, would be a prime candidate for an unnova remnant. It would be the ghost of a giant finally revealing itself not by the light it emits, but by the light it bends, a permanent echo of the supernova that never was. But what if the ultimate cosmic phantom wasn't lurking in a distant nebula or at the heart of another galaxy, but was our near neighbor hiding in the stellar backyard of our own solar system? Imagine a dark star passing within a few hundred light years of Earth, a silent, massive presence so close that its gravitational influence could be subtly tugging on the stars we see every night. This isn't just a thrilling thought experiment, it's a serious possibility that astronomers are investigating right now, using the most detailed map of our galaxy ever created. The search for this solar neighbor begins with painstaking analysis of data from the European Space Agency's Gaia mission. Gaia is not a traditional telescope that takes pretty pictures. It's a precision astrometry machine, meticulously measuring the positions, distances, and motions of over 1 billion stars in the Milky Way with unparalleled accuracy. It's essentially creating an ultra-high-definition movie of our galaxy's evolution. By tracking the minute movements of these stars, scientists can detect the slightest gravitational tugs, the telltale wobbles that suggest an unseen object is pulling on them. Already, this data has revealed thousands of new binary star systems where one partner was too faint to see. But what if some of these wobbles can't be explained by a faint star or a large planet? What if the anomaly points to something with the mass of a star but emits no light at all? These gravitational whispers in the Gaia data are our first clues that a dark star might be closer than we ever imagined. The immediate challenge for astronomers is distinguishing a true dark star from a more mundane, though still fascinating, object, a brown dwarf. Brown dwarfs are often called failed stars. They form like stars but never accumulate enough mass to ignite sustained hydrogen fusion in their cores. They are large, massive, and incredibly faint, glowing only with a dim, residual heat that makes them very difficult to detect. A cold, ancient brown dwarf that has radiated away most of its warmth could easily mimic the gravitational signature of a theoretical dark star. The key to telling them apart lies in a multi-wavelength hunt. If Gaia points to an unseen mass, the next step is to train every available instrument on that patch of sky. The James Webb Space Telescope, with its incredible infrared sensitivity, would be tasked with looking for any faint heat signature. Finding even the dimmest glow would confirm a brown dwarf. Finding absolute nothingness, a complete void where gravity says something massive must be, would be the first step toward confirming a genuine dark star. Discovering a dark star in our cosmic neighborhood would be the scientific opportunity of a millennium, offering a chance to study one of these objects up close without the interfering noise of a crowded galactic environment. We could measure its mass with incredible precision by observing how it gravitationally lenses the light of background stars, potentially allowing us to probe its internal structure. We could study its influence on the sparse gas of the interstellar medium, watching how it sculpts a local environment without the light of a stellar wind. Most importantly, its proximity would make it the perfect laboratory for solving the dark matter puzzle. We could search for signs of a concentrated dark matter halo around it, something that would be impossible to distinguish around a distant object. By studying how this halo gravitationally influences the object itself and its immediate surroundings, we might finally get direct, localized evidence for how dark matter behaves and interacts with itself. The mere possibility that such an object could be so close is a profound reminder of how much of our universe remains hidden from our eyes. It suggests that the cosmic inventory of our local neighborhood is still incomplete, and that the darkness between the stars is not empty, but potentially filled with silent, massive neighbors we are only just learning how to see. Finding one would transform it from a theoretical specter into a tangible cosmic destination, a permanent fixture in our sky that we cannot see, but whose presence would forever change our understanding of our place in a dark and mysterious universe. Our journey now leads us to an object that represents the ultimate test of our observational ingenuity, a dark star that may only reveal itself not through a single signal, but through a chorus of whispers across the entire spectrum of physics. This is the multi-messenger candidate, a hypothetical dark star whose profound influence is predicted to leave its mark not just on light, but on the very fabric of space-time and the most elusive particles in the universe. Its detection would mark the dawn of a new era, one where we no longer just look at the cosmos, but truly listen to it in all its strange and wonderful languages. The core concept of multi-messenger astronomy is a coordinated symphony of observation. Instead of relying on a single telescope or technique, it calls upon a global network of instruments, each designed to detect a different type of signal. For this particular dark star, the primary hypothesis suggests it is not a solitary object, but one half of a binary pair, slowly spiraling toward a cataclysmic merger with another massive dark remnant. This slow cosmic dance, which could last for millions of years, is what generates the multiple messengers we hope to detect. Each signal provides a different piece of the puzzle, and only when combined do they reveal the full, spectacular picture. The first and most persistent signal would be gravitational waves. As these two massive objects orbit one another, they ripple the fabric of space-time itself, sending out waves that propagate across the universe at the speed of light. Observatories like LIGO, Virgo, and the future space-based LISA are exquisitely tuned to detect these ripples. The signal from such a binary would be a very specific chirp, a continuous wave that steadily increases in frequency and amplitude as the orbit decays, potentially detectable for years before the final merger. This long-duration signal would allow astronomers to precisely pinpoint the location of the system in the sky and accurately calculate the masses of the two objects, providing the first crucial data points. The final act of this drama, the merger itself, would unleash a much more powerful burst of gravitational waves, a final scream of space-time distortion. But it could also produce a second, even more elusive messenger, neutrinos. These ghostly particles, which barely interact with matter, are produced in incredible numbers during the most violent events in the universe. The total collapse of two dark stars into one would be a neutrino factory. While most would stream away undetected, a next-generation detector like Hyper-Kamiok or the Ice Cube Neutrino Observatory at the South Pole could potentially catch a significant burst of these particles arriving at Earth within a tiny window of time, mere seconds after the gravitational wave signal peaks. Catching both signals together would be like getting an invitation and then hearing the starting gun for the main event. But the multi-messenger approach doesn't stop there. Even though the objects themselves are dark, their merger could potentially create a transient, observable electromagnetic signature. The violent collision could shock heat any wispy interstellar gas in their immediate vicinity, creating a brief, faint flash of light in the optical or ultraviolet range. Alternatively, the formation of a new, more massive dark remnant could trigger the sudden accretion of nearby matter, sparking a short-lived radio or X-ray flare. This would be the weakest signal, incredibly challenging to detect, but it would provide the final, confirming piece of evidence, directly linking the gravitational and neutrino events to a specific tiny point in the sky. The global campaign to find such an object is already underway, a testament to international scientific collaboration. When a promising long-duration gravitational wave signal is identified, an automated alert is sent to observatories around the world and in space. Optical telescopes swivel to that sector of the sky, taking rapid, sequential images to hunt for any new point of light. Radio dishes scan the area for unusual static. X-ray and gamma-ray satellites monitor for high-energy bursts. Neutrino detectors stand by, their data streams meticulously analyzed for a correlated spike. This is astronomy in its most active, vigilant form, a 24/7 watch for the universe's most secretive events. Discovering a dark star through this coordinated, multi-messenger effort would be nothing short of a revolution. It would validate this entire interdisciplinary approach, proving that we can successfully triangulate the universe's most hidden phenomena. The data would provide an unprecedented test of general relativity under the most extreme gravitational conditions imaginable. It could finally answer questions about the true nature of these dark remnants. Are they all black holes with event horizons, or could some be even more exotic objects like boson stars or gravastars? Each messenger, the gravity, the neutrinos, the light, would tell a different part of the story, and together they would write a new chapter in our understanding of how mass, energy, and space-time interact in the darkest corners of creation. But perhaps the most mind-bending possibility of all is that a dark star, an object born from the ultimate defeat of light, could itself become the sun for a whole new family of worlds. This isn't just a flight of fancy. The physics of planetary formation might not care if the central anchor is bright or dark, only that its gravity is powerful enough to shape a system. Imagine a vast, cold accretion disk of gas and dust, the leftover material from the dark star's own formation, or captured later from an interstellar cloud slowly circling this gravitational abyss. In the frigid quiet, far from the heat of nuclear fusion, particles would still collide, stick together, and gradually build up into planetesimals, then protoplanets, and finally, fully fledged worlds. These would be planets unlike any we know, born and nurtured in permanent twilight, their existence dictated solely by the relentless pull of their invisible sun. The conditions on such a world would be the definition of exotic. Without a source of stellar warmth, the surface of any planet would be a frozen wasteland, plunged into temperatures only a few degrees above absolute zero. The very concept of a day and night cycle would be meaningless. The sky would be a permanent, star-studded blackness, with the dark star's location betrayed only by the precise motions of the other planets in the system, a grand celestial clockwork with an empty center. Any atmosphere would long since have frozen solid, coating the surface in layers of nitrogen, oxygen, and argon ice. The landscape would be sculpted not by wind and water, but by the slow, gravitational cracking of the crust and the occasional impact from rogue comets also bound to the dark star's influence. And yet, against all odds, the potential for life might not be completely extinguished. The most promising habitat wouldn't be on a cold, surface world, but deep within the icy mantle of a moon similar to Jupiter's Europa or Saturn's Enceladus. The key is tidal heating. If a planet or moon orbits close enough to the dark star and its path is perturbed by the gravity of sibling planets, the constant flexing and squeezing of its interior could generate enough geothermal energy to maintain a vast subsurface ocean of liquid water. In this lightless, abyssal sea, sealed away from the frozen surface above, life could potentially arise and thrive, fueled not by sunlight, but by chemosynthesis around hydrothermal vents on the ocean floor. Entire ecosystems could exist in this eternal darkness, completely unaware that their entire world orbits a perfect void, a sun that never was. Detecting such a system requires us to think like detectives of gravity and faint heat. The primary method would once again be gravitational microlensing. If a dark star with planets passes in front of a distant background star, the complex interplay of its gravity and that of its orbiting worlds would create a distinctive, multi-peaked brightening in the background star's light. Sophisticated algorithms can decode this light curve, revealing not only the mass of the central dark star but the number, masses, and orbital distances of its planets. It would be a full planetary census conducted entirely through the warping of space-time. For a closer system, we might have a second option, looking for the faintest whisper of heat. While the dark star itself is cold, any large gaseous planets that formed recently in the last few billion years might still retain a significant amount of internal heat from their formation. To our most sensitive infrared telescopes like the James Webb, these worlds might appear as extremely faint warm points huddled around a precise, empty point in space. Pinpointing several such warm objects moving in concert around a common, invisible center of gravity would be compelling, albeit indirect, evidence of a complete dark solar system. The discovery of even one planet orbiting a dark star would profoundly expand our understanding of where life could potentially exist. It would sever the last remaining tether between habitability and starlight, suggesting that life could emerge in the most isolated, light-starved corners of the galaxy, warmed only by the internal heart of a world and the gravitational embrace of a silent, dark sun. It would mean the universe's biological potential isn't limited to the golden zones around friendly stars, but might also flourish in the deep freeze, in abyssal oceans hidden beneath ice, forever circling the ultimate paradox, a life-giving world orbiting a star that gives no light at all. To find a dark star, you might instinctively look toward the quiet, empty reaches of space, but some of the best hiding places are actually in the most chaotic and brilliant corners of the cosmos. Imagine a galaxy in the throes of a ferocious, explosive tantrum, a place where stars are being born not in gentle nurseries but in a frantic, violent frenzy. This is the environment of a starburst galaxy, and one of the most famous is Messier 82, a celestial powerhouse where the entire core is ablaze with the light of millions of new stars. It is here, in this maelstrom of creation, that we find our next candidate, a dark star whose origin story is written in fire and chaos, a phantom born from the most extreme stellar pressures imaginable. The core of a galaxy like M82 is a fundamentally different kind of place. It's not just a busy star-forming region, it's a cosmic pressure cooker. Triggered by a close encounter with a neighboring galaxy, vast waves of interstellar gas have been funneled into the galactic center, creating densities of raw material thousands of times greater than we see in our own quiet corner of the Milky Way. In this ultra-dense environment, star formation doesn't follow the gentle rules we're used to. Instead of isolated clouds collapsing peacefully, everything happens at once and on a monumental scale. Giant molecular clouds collide and merge, triggering chain reactions of collapse that birth massive star clusters in an instant. It's a top-down, explosive process where the default outcome isn't a humble star like our Sun, but a legion of stellar titans, many destined for short, violent lives. This relentless production of massive stars is the key ingredient for creating a dark star here, as the sheer statistical probability of a rare, direct collapse event skyrockets in this frantic environment. Spotting a single dark star against the blinding backdrop of M82 is arguably the greatest observational challenge on our list. The galaxy's core is a blazing inferno of ultraviolet and infrared radiation, outshining entire normal galaxies. It's a swirling storm of glowing gas, dark dust lanes, and the brilliant, short-lived supergiant stars that define a starburst. Trying to find the gravitational signature of one invisible object in this luminous hurricane is like trying to single out the footprint of one specific raindrop in the middle of a monsoon. Every known wavelength is flooded with light and energy from other processes. The intense radiation from countless supernova and stellar winds creates a constant, high-energy background static that drowns out any faint, telltale X-ray signature a passive dark star might lack. Even the subtle wobbles of visible stars would be nearly impossible to track with precision amidst such turbulent and crowded conditions. So how do we hunt for a phantom here? Astronomers must become experts in reading the subtle language of motion and structure within the chaos. The primary strategy involves using powerful radio telescope arrays, like the Atacama Large Millimeter Array in Chile, to peer through the visible turmoil and map the cold, dense molecular gas that fuels the starburst. By creating exquisitely detailed three-dimensional velocity maps of this gas, scientists can search for peculiar, localized disturbances, swirling vortexes, or convergent flows that shouldn't be there. In a region where everything is moving violently due to supernova shocks and stellar winds, finding a point like gravitational sink, a silent anchor that is pulling gas inward in a distinct pattern, would be a huge red flag. It would be the signature of a massive, compact object holding its ground amid the storm, its gravity creating a quiet eddy in the energetic flow. Furthermore, the very evolution of the starburst itself might hold clues to the presence of these dark remnants. The incredible rate of star birth in M82 cannot last forever. It's a flash in the pan that will eventually consume all its available gas and burn itself out. Theoreticians running sophisticated computer simulations of these environments have found that the presence of a number of massive dark stars can dramatically alter how this plays out. Because they form from direct collapse without a supernova, they lock away an enormous amount of mass permanently, removing it from the cycle of star formation. This means less gas is available to form the next generation of stars, and less material is being recycled and enriched by supernova explosions. A starburst galaxy that seems to be shutting down its star formation faster than the models predict could be hinting that a population of dark stars is silently sequestering its future fuel. Discovering a dark star in a place like M82 would do more than just add another object to our list. It would reveal a fundamental aspect of how galaxies evolve under extreme conditions. It would prove that the initial mass function, the rulebook for how many big versus small stars are born, can be radically different in these environments, skewing heavily toward producing monsters. Some of those monsters live fast, die young, and explode, while others might simply vanish, leaving behind massive dark ghosts that continue to shape their galaxy's destiny through their gravity alone. This candidate represents the ultimate cosmic paradox, an object born from the most intense, luminous firestorm in the universe, whose final state is one of perfect, immutable darkness, a silent testament to the violent beauty of a starburst. Yet as we push the boundaries of what a dark star could be, we inevitably arrive at a critical and fascinating frontier, the theoretical limits that separate these enigmatic objects from the more familiar dark inhabitants of the cosmos, namely black holes and neutron stars. This isn't just a matter of simple categorization. It's a journey into the gray areas of astrophysics, where the definitions blur and our current understanding of physics is stretched to its breaking point, potentially requiring entirely new laws to describe what's truly happening. The most fundamental dividing line is the event horizon, that infamous point of no return that defines a black hole. According to general relativity, once matter collapses within its own Schwarzschild radius, an event horizon must form, and anything that crosses it is lost to our universe forever. But what if that isn't the absolute end of the story? Some theoretical models propose objects that walk right up to this line without ever quite crossing it. Imagine a star so incredibly dense that light struggles to escape, taking years to climb out of its immense gravitational well, making the object appear dark and frozen from an outside perspective, yet it never quite forms a true event horizon. These proposed entities, sometimes called gravastars or dark energy stars, would have a surface instead of an infinite void, potentially made of an exotic form of energy or matter that halts the collapse at the very last possible moment. They would mimic a black hole in almost every way, bending light and trapping matter with their gravity, but they would lack the one defining feature we use to identify a black hole. Telling the difference between a true black hole and one of these imposters is one of the greatest challenges in modern astronomy, as both would appear as simple, silent gravitational points in the void. The mass of an object also provides a crucial clue, but even here the lines are wonderfully fuzzy. We know the rough mass ranges for neutron stars typically between 1 and 2.2 solar masses, and for stellar mass black holes, which generally start around 5 solar masses. This leaves a mysterious gap between roughly 2.2 and 5 solar masses, a range where we aren't entirely sure what forms. Could this be the natural home for a certain class of dark stars? Furthermore, the formation pathway is just as important as the final mass. A neutron star is the remnant of a classic supernova explosion. A black hole can form from a supernova or, as we've discussed, from a direct collapse. A dark star, in many theories, is the product of that direct collapse, a silent failure that leaves behind a remnant that could fall anywhere within that mass gap or even far beyond it, depending on the size of its progenitor star. This means a dark star could, in theory, have the mass of a typical black hole but a completely different internal structure, a possibility that forces us to question whether mass alone is a reliable label for these objects. Perhaps the most mind-bending possibility is that dark stars might not be made of the stuff we know at all. Neutron stars and black holes are ultimately made of ordinary matter, protons, neutrons, electrons, that have been crushed into extraordinary states. But some theories suggest dark stars could be composed of something truly exotic, like a Bose-Einstein condensate of fundamental particles, or even a soup of free-floating quarks not confined within neutrons. These theorized objects with names like quark stars or boson stars would be held up against total collapse not by nuclear forces or electron degeneracy pressure, but by entirely new quantum mechanical rules. A boson star, for instance, could be a gigantic, diffuse sphere of invisible particles acting as a single quantum wave, possessing the mass of a black hole but spread over a much larger volume with no sharp surface or central singularity. Distinguishing such an object from a black hole through observation alone would be incredibly difficult, as its gravitational signature could be nearly identical, forcing us to rely on the most minuscule of differences in how it lenses light or interacts with other matter. This entire exploration brings us to the humbling realization that our current taxonomy of cosmic objects might be incomplete. We have categories for what happens when collapse is halted by neutron degeneracy pressure, a neutron star, and for when collapse is complete, a black hole. But we may lack the language and the physics for all the possibilities in between, the states of matter that are stable against gravity for reasons we haven't yet discovered. The hunt for dark stars is therefore more than a search for hidden objects. It is a direct test of our physical models at their most extreme. Finding an object that defies classification, one that has the mass of a black hole but doesn't behave like one, would be the clearest signal that we are on the precipice of a new physics, staring into a darkness that holds not just answers but deeper, more profound questions about the very fabric of reality. But to turn these theoretical whispers into confirmed detections, we need a new class of explorer, not just telescopes, but gravity detectives armed with technology so advanced it borders on science fiction. This is the era of the future hunters, a global fleet of next-generation observatories specifically designed to see the unseeable, each one tuned to a different facet of the dark star mystery, finally giving us the tools to lift the veil on these cosmic phantoms. Leading the charge in the wide-angle survey is the Nancy Grace Roman Space Telescope, named for NASA, a first chief astronomer. While the James Webb Telescope is a powerful zoom lens focused on the deepest reaches of time, Roman is a breathtakingly wide-angle camera designed to capture enormous swaths of the sky in a single, exquisite snapshot. Its primary mission in this hunt is a monumental microlensing survey, a task for which it is perfectly suited. Roman will continuously monitor hundreds of millions of stars toward the galactic bulge, the crowded central region of our Milky Way. It will watch for the telltale symmetric brightening of a background star, the signature of an invisible foreground object bending its light. Because of its wide field of view and incredible precision, Roman is expected to detect thousands of these microlensing events. But astronomers aren't just looking for any event. They are on the hunt for the anomalies, the events that last for an unusually long time, indicating a very massive lens, and those that occur in seemingly empty space far from any visible star. These outliers in the data could be our first statistical proof of a population of dark stars, their mass and abundance finally quantified not by their light but by their shadow. While Roman scans the skies for these solitary ghosts, another revolutionary mission will be listening for the cosmic duets. The Laser Interferometer Space Antenna, or LISA, is not a telescope at all, but the first dedicated gravitational wave observatory to be placed in space. Scheduled for launch in the next decade, LISA will consist of 3 spacecraft flying in a perfect triangular formation millions of miles apart, connected by lasers. This vast configuration allows it to detect a much lower frequency of gravitational waves than ground-based detectors like LIGO can. This is the key. While LIGO hears the final, frantic seconds of a merger between stellar mass black holes, LISA will be able to listen to the years, decades, or even centuries-long gravitational wave hum produced by binary systems containing massive dark stars as they slowly spiral toward each other. It will essentially hear the entire cosmic symphony of their dance, not just the final crashing chord. This long-duration signal will provide an incredibly precise map of the system's masses, orbits, and locations, allowing optical telescopes to swing toward the spot and search for any faint electromagnetic counterpart, turning a gravitational whisper into a confirmed celestial address. On the ground, the hunt will be taken up by a behemoth known as the Einstein Telescope, envisioned as a subterranean observatory with arms 10 times longer than LIGO. This future project is designed to be infinitely more sensitive. Its improved design will allow it to peer deeper into the universe and detect far fainter gravitational wave signals, potentially picking up the mergers of primordial dark stars from the very dawn of time. Furthermore, its enhanced sensitivity could allow it to detect the continuous gravitational waves emitted by a lone, spinning dark star that isn't perfectly spherical, a tiny, persistent hum from a rotating mountain on an object just a few miles across but containing the mass of several suns. Hearing that specific tone would be like identifying a person by their unique voice in a crowded room, providing direct insight into the structure and composition of the object itself. The true power of these future hunters, however, will be realized not in isolation but in concert. The most compelling dark star discovery will likely be a multi-messenger event, a celestial story told through different chapters arriving at Earth at the same time. Imagine LISA detecting the persistent gravitational wave hum of a binary dark star system slowly decaying. Alerts are sent out across the astronomical community. The Nancy Grace Roman Telescope, already scanning that region, checks its archival data and finds a corresponding microlensing event that precisely matches the mass and location predicted by LISA. Meanwhile, the James Webb Space Telescope turns its infrared gaze toward the spot, confirming the utter absence of any thermal signature. Finally, as the two objects merge, the Einstein Telescope catches the crescendo of gravitational waves, while a neutrino observatory records a coincident burst of ghost particles. This symphony of data, collected across the entire spectrum of physics, would not just announce the discovery of a dark star. It would provide a full anatomical study, revealing its mass, spin, composition, and origin story, finally pulling the phantom out of the shadows and into the light of human understanding. Yet for all their mystery, dark stars might represent more than just hidden mass. They could be the key to unlocking the deepest secret in the universe, the true nature of dark matter itself. This connection weaves through several compelling theories, the first being that dark stars could be made of dark matter. Imagine a star forming in the early universe from a cloud of pure hydrogen and helium. But this cloud is also infused with a high density of a hypothetical type of dark matter particle known as a WIMP, a weakly interacting massive particle. As the protostar begins to condense, these WIMP, drawn by gravity, also accumulate at its core. Here's where the magic happens. Unlike normal matter, these dark matter particles can annihilate with each other upon collision, a process that releases a tremendous amount of energy as heat. This exotic form of fusion could potentially power a star, not with nuclear fires, but with a steady, dark energy source radiating from its heart. This theoretical object would be a true dark star, shining not from proton-proton chains, but from the silent annihilation of matter we cannot see, offering a completely new and stable stellar architecture that could have existed in the universe's infancy. Even if dark stars aren't powered by dark matter, their immense gravity would make them incredible natural traps for it. Any massive object creates a gravitational well, and dark matter, responsive to gravity, would be drawn toward it, forming a concentrated halo around the star. In the crowded disk of a galaxy, measuring the specific dark matter halo around a single star is impossible. Its signal is lost in the galaxy's overall dark matter distribution. But a dark star, especially one adrift in the intergalactic void like our earlier candidate, the silent sentinel, offers a perfect, isolated laboratory. With no other significant mass for millions of light years, its personal dark matter halo would be the only game in town. By meticulously studying how such a star gravitationally lenses the light of background galaxies, astronomers could look for subtle deviations in the lensing effect, tiny anomalies that betray the specific density and distribution of the dark matter clumped around it. This would give us our first ever direct measurement of how dark matter behaves on a small scale, revealing whether it is cold and clumpy as leading models suggest, or if it has more complex, self-interacting properties. The implications of this connection are staggering, suggesting that the hunt for dark stars is a two-for-one cosmic deal. Finding one wouldn't just solve the mystery of these invisible giants, it would simultaneously provide a powerful new tool for dissecting the properties of dark matter. A confirmed detection would allow us to study dark matter's interaction cross-sections, how likely particles are to bounce off each other by observing how the halo responds to the star's gravity. It could even help us pinpoint the mass of individual dark matter particles by analyzing the halo's structure. In this way, a dark star ceases to be merely an object of curiosity and transforms into a bridge, a cosmic translator that allows us to interpret the invisible forces that bind the universe together, turning one profound mystery into the solution for another. Yet the allure of these cosmic phantoms extends far beyond the pages of astrophysics journals, weaving its way into the very fabric of our culture and philosophy. Long before the term dark star entered the scientific lexicon, humanity was already gazing into the heavens and sensing a hidden presence, giving form to that emptiness through myth and story. Ancient cultures often populated the void with creatures of shadow and mystery. The great serpent Apophis in Egyptian mythology was a demon of darkness who sought to extinguish the sun god Ra each night, an eternal personification of chaos lurking just beyond the light. In many creation myths, the universe itself is born from a formless, dark void, the Greek chaos, the Norse Ginnungagap, a primordial nothingness that held the potential for everything. These stories reveal a deep, intuitive understanding that the darkness is not merely an absence, but a presence, a canvas upon which both gods and monsters are painted, a concept that finds its modern parallel in the enigmatic dark star. This cultural fascination exploded into the popular imagination with the dawn of the science fiction genre, where the dark star became a powerful metaphor for the unknown and the unknowable. Perhaps the most iconic example is Gregory Benford's 1997 novel Foundation Sphere, where a hidden dark star named Nemesis on a long, elliptical orbit around our sun becomes the catalyst for galactic intrigue. The name itself is profoundly telling. Nemesis, the Greek goddess of retribution, an unseen force of destiny whose inevitable return brings calamity. This trope of the dark star as a hidden, impending threat taps into a deep-seated human anxiety about what might be lurking in the vast, unexplored spaces just beyond our sight, a cosmic embodiment of the fear that our understanding of the universe is fundamentally incomplete. But science fiction has also explored the concept with a sense of profound wonder and existential curiosity. The film Event Horizon presented a fictionalized, terrifying version of a dark star's gravitational power, imagining a ship that could create an artificial singularity and inadvertently open a gateway to a hellish dimension. While not scientifically accurate, the core idea that extreme gravity could tear a hole in the fabric of reality and expose us to forces beyond our comprehension resonates with the genuine mystery surrounding these objects. In a more contemplative vein, authors like Alastair Reynolds have used the idea of ancient, hidden relics, dark stars or their exotic equivalents, as plot devices that force humanity to confront its own insignificance in a cosmos filled with wonders and horrors from a time before planets formed. These stories use the dark star not as a monster, but as a key, a catalyst that unlocks a larger, more terrifying, and more magnificent universe. Philosophically, the dark star challenges our most basic assumptions about existence and reality. It is the ultimate embodiment of the philosophical concept of the noumenon, a thing as it is in itself, independent of our perception. We can only know the dark star through its effects, through the gravitational ripples it creates in the phenomenal world of light and matter. It is a permanent reminder of the limits of human observation, that there are things which truly exist, which have mass and shape and influence the cosmos, yet which remain forever outside the realm of direct human experience. This forces a humbling conclusion. The universe does not require an observer to be real. It is complete and entire in itself, filled with entities that defy our need to see and categorize, existing in a state of pure, objective reality whether we are there to witness them or not. This ties directly into our understanding of the universe's hidden aspects, particularly the enigma of dark matter. Just as the dark star is detected only by its gravity, so too is the vast majority of matter in the universe believed to be invisible, detectable only by its gravitational pull on galaxies. The dark star, therefore, becomes a tangible, localized analog for the cosmos's greatest secret. It is a point of focus that makes the abstract, diffuse concept of dark matter feel more concrete. By hunting for these objects, we are not just searching for strange stellar remnants. We are practicing for the larger hunt, developing the tools and the mindset needed to map the invisible scaffolding of all creation. The dark star is a gateway concept, training our minds to accept that what is most real and most powerful in the universe may also be what is most hidden from our senses. Ultimately, the enduring power of the dark star in our collective imagination is a testament to its perfect duality. It is both a specific astrophysical hypothesis and a boundless cultural symbol. It represents the terror of the unseen void, but also the thrilling promise of discovery. It is a reminder of our own fragility and ignorance, but also a beacon driving us toward greater understanding. The human mind is wired to fear the dark, but it is also wired to be curious about it, to venture into the shadows with a lantern held high. The dark star is that shadow and that lantern combined, a mystery that compels us to search, a silence that begs to be heard, and a permanent testament to the fact that the universe's greatest stories are not always written in light. And now we arrive at the ultimate cosmic ghost, a theoretical construct so perfectly elusive it represents the pinnacle of this entire mystery. This isn't merely another dark star candidate. It is a perfect storm of invisibility, a hypothetical object that combines the most challenging properties from across our list into a single entity that defies detection on every conceivable level. Imagine a primordial dark star, born from the direct collapse of a pristine gas cloud in the early universe, composed of pure hydrogen and helium. It possesses the immense mass of the veiled titan of Andromeda, yet it has been flung from its birthplace by a gravitational slingshot, becoming a rogue wanderer in the intergalactic void like the silent sentinel. It is not just a cold, passive object. It is a magnetic monster with an unimaginably powerful field that has aligned its poles perpendicular to our line of sight, ensuring its faint synchrotron radiation sweeps uselessly through empty space, never reaching our telescopes. To complete its perfect camouflage, it drifts through a region like the Boötes void, where there are no background stars to lens and no interstellar gas to accrete, leaving no possible footprint on its environment except for its sheer, silent gravity. This is the ultimate cosmic ghost, an entity defined not by what it is, but by what it lacks: light, location, interaction, and any discernible signature beyond the most fundamental force in the universe. The profound challenge of finding such an object forces us to confront the very limits of the scientific method. How do you prove the existence of something designed by nature to leave no proof? Our current detection strategies all rely on the object betraying its presence through some secondary interaction, bending light, rippling space-time, or heating a wisp of gas. The ultimate ghost would do none of these things in a way we could perceive. Its gravitational influence would be so isolated and uniform that it wouldn't create the microlensing events we know how to look for. Its journey through the perfect emptiness of the void would generate no friction, no shock waves, no sound. It is the universe's most perfect secret, a monument to its own hidden nature. To even conceive of a search pattern, we would need to move beyond mapping what is there and instead begin meticulously cataloging the gravitational anomalies of nothingness, searching for the subtle, persistent warping of the cosmic vacuum itself, a task that may require technologies and theoretical frameworks we have not yet even dreamed of. Yet, the philosophical implications of its potential discovery are even more staggering than the technical hurdles. Finding this ultimate phantom would be the most powerful experimental evidence ever obtained for the philosophical concept of realism, the idea that the universe exists independently of our observation of it. Here would be an object of immense mass and scale that has never interacted with light or matter in any significant way since its formation over 13 billion years ago. It has existed in a state of pure being, utterly indifferent to and unaware of the unfolding cosmic drama of galaxies, stars, planets, and life. Its existence would be a silent, profound testament to the fact that reality is complete without us. The cosmos does not require a witness, it simply is. This would fundamentally reshape our understanding of our place in the universe, not as central observers for whom the cosmos manifests, but as fleeting inhabitants of a reality that is overwhelmingly and permanently beyond our perception. For science, its discovery would be nothing less than a second Copernican revolution. Just as Copernicus moved us from the center of the solar system, this would move us from the center of perceptible reality. It would prove that our census of the cosmos, built entirely on the electromagnetic spectrum, is not just incomplete, it is perhaps a mere footnote to a much larger, darker, and more massive hidden universe. Our textbooks, our models, our entire understanding of stellar evolution and galactic structure would require a fundamental rewrite from the ground up, starting with the humbling admission that we have been studying only the luminous froth on a vast, dark ocean. This one discovery would open up an entirely new frontier of physics, dedicated to studying the properties, formation, and distribution of objects that we can never see, only infer through their most subtle gravitational whispers. Ultimately, the quest for this ultimate dark star is about more than astronomy. It is a fundamental human pursuit. It represents the absolute outer limit of our curiosity, our relentless drive to know the unknown, even when the universe seems deliberately designed to keep its secrets. The hunt itself, with its need for ever more ingenious technology and profound theoretical leaps, is a catalyst for our own evolution as a species. It pushes our intellect, our engineering, and our imagination to their breaking points. Whether we ever find this perfect ghost is almost beside the point. The act of searching for it forces us to expand our definition of what is real and possible, compelling us to build better tools and ask deeper questions. In looking for the absolute darkness, we are ultimately shining the brightest light on our own potential, reaching for a truth that lies in the void, not because it is easy, but because it is the hardest and most rewarding challenge the universe has to offer. From the silent, lurking phantom in Orion's glowing nursery to the ancient, wandering relics cast out into the intergalactic void, these 25 candidates represent more than just a list of cosmic suspects. They are a testament to the breathtaking diversity of what might be hiding in the dark. We've journeyed through brilliant galactic cores and into the heart of lightless nebulae, explored the possibility of dark planets and phantom binaries, and even considered stars that might be powered by the annihilation of dark matter itself. Each candidate, from the magnetic monster to the ultimate cosmic ghost, offers a different puzzle, a unique set of clues, and a thrilling possibility for rewriting the rules of astrophysics. This isn't a single mystery, but a whole spectrum of enigmas, each one challenging us to look at the universe in a completely new way, and proving that the greatest stories are often the ones written in gravity, not in light. The sheer variety of these theoretical objects is what makes this hunt so electrifying. It shows us that the universe's creativity doesn't end with the stars we can see. It has a hidden workshop where it forges things stranger and more magnificent than we ever imagined, objects that are cold, dark, and yet unimaginably powerful. The fact that we can even propose such ideas, using the delicate tools of mathematics and inference to paint pictures of things we've never directly seen, is one of the most profound achievements of the human mind. It's a celebration of curiosity itself, of our refusal to accept that the visible universe is all there is. This search pushes our technology to its absolute limits and our theories to their breaking points, and that is exactly where the most exciting discoveries are always made. So as we look up at the night sky, let's remember that the darkness between the stars is not empty. It is a canvas for possibilities, a frontier waiting to be mapped by the gravity detectives of the future. Stay curious, because every time we point a new telescope at the heavens or detect a new ripple in space-time, we are peeling back another layer of this incredible cosmic mystery. The universe is whispering its secrets in the language of mathematics and gravity. We just have to learn how to listen more closely. Now we want to hear from you. Which of these dark star candidates captures your imagination the most? Does the idea of the quasar imposter hiding in plain sight fire up your sense of cosmic wonder? Or does the thought of a vampire dark star slowly feeding in a silent binary send a chill down your spine? Share your favorite theory or your own wild speculation in the comments below. We read every single one. And if you're ready to join us on the next adventure to the edge of discovery, make sure to subscribe and hit the bell so you don't miss our deep dives into the universe's greatest secrets. The darkness holds so much